Hi, I'm Debbie Nelson with Nixene Publishing. I'm a contributing editor and project manager here in the United States, coming to you from the Mississippi Gulf Coast. And we have with us today Adrian Nixon, who is the editor-in-chief of the Nixene Journal over in Yorkshire, England. Adrian, hello.
Hello, Debbie. Nice to see you again.
Well, it's nice to see you too, especially because we have such an exciting episode of our video series on graphene. Um, you may remember from another video that we were talking about a new superlative that graphene has been given just this year in 2020, and there's actually another one. So today we're going to be talking about it. It is the impermeability of graphene. So Adrian, please tell us what's going on.
We're recording this, Debbie, just at the end of June 2020, and this work is based on a paper that was produced in Manchester on the 11th of March 2020. So this is just weeks old. So what the research has done, I'll share my screen again, shall I? And
Please do.
this was done at the NGI in Manchester. So I'll just pick this and share that. You can see a white screen again, can you, Debbie?
Absolutely.
Good, we're good to go then. So this is the NGI, the National Graphene Institute, on the campus of the University of Manchester in the UK. And this is sort of Graphene Central. This is where the Nobel Prize winners live and work. And this is basically a 60 million euro facility. And it's full of some of the world's best kit, and it goes down under the basement as well. And there are some fantastic laboratories down there where guys in blue suits in clean rooms stare down microscopes and play around with graphene. And what we can see here is some of those labs under the NGI. These are the clean room facilities. These are some of the actual researchers. So they've been using some of this kit to actually do the work that we're about to have a look at. Does that sort of give a feel for where this work was done, Debbie?
Yes, absolutely. NGI has a great reputation for.
Yeah, worldwide. Yeah, Centre of Excellence. It is world class. So what the researchers have done, I'll have to put it into graphics rather than photographs because it just gets far too complicated and you can't see what's actually going on if we just stuck with photographs. So again, I've got one of my slides which builds, and you remember last time we talked about a superlative, which was fatigue resistance of graphene.
Yes.
This work is very similar because you made reference to this work when we were talking about fatigue resistance. Because again, what's going on here is the researchers have laid a single sheet of graphene. This is perfect graphene from a single crystal, laid over a circular hole that's been drilled into hexagonal boron nitride or graphite. The researchers actually use both. And they use an atomic force microscope. This is basically, you can think of this as a very expensive, very sensitive pointy stick where you can measure the height that the stick moves with atomic precision. So if you can imagine, you know when you get layers of copier paper, Debbie, and if you sort of spread them out so the edge is stepped, you can run your fingernail down the edge and you can count the number of sheets of paper there are. Yeah, that makes sense?
Yes, yes.
Well, an atomic force microscope sort of works the same way, except that fingernail is replaced by this pointy bit here, and it can tell one of those clicks between a layer of a height of one atom.
Oh my goodness.
It's incredibly sensitive. So what's actually going on here is it's able to tell the difference in movement with atomic scale precision, the height of that graphene membrane. So what the researchers did was they laid perfect sheets of graphene over these holes, and they started off by filling the hole in here with a gas, in this case helium, and they had exactly the same pressure as outside. So all other things being equal, that graphene layer would be really flat. However, if any gas molecules went through the graphene layer into the outside, there'd be less inside here than there were outside, and that would create a pressure which would force the graphene layer down, and you'd be able to measure that with the atomic force microscope. Does that make sense so far?
Yes, yes.
Great. And then conversely, if the graphene was permeable and gas molecules could go from the outside in, it would make that layer balloon up over the hole. And again, you'd be able to measure that difference with the atomic force microscope. So can you see we've got a very precise way of measuring whether or not this seal that you can put across the top is a perfect seal or not with atomic scale precision.
Yeah, absolutely. And atomic scale precision says a lot for the people who invented that piece of machinery.
Yeah, they had to. Yes, you're quite right, Debbie. They had to invent this piece of machinery. Yes, to make this, and this is all done by staring down microscopes to actually make this stuff work and to construct this. So just actually building these things is an astonishing feat of scientific engineering. It's really good. Plus the fact, the original paper, by the way, which the paper references down here, is really well worth a read. It's one of the most enjoyable papers I've had to read for a long time. It's put together like a Swiss watch. For those of you interested in experimental design, well worth a read. This is really top quality stuff. So what did they find? Well, they found that graphene was so impermeable to gases from helium upwards. So when you're dealing with helium gas, one atom thick layer, the one atom thick layer of graphene was so impermeable to helium that no gas molecules would probably come out for the entire edge of the universe. It was like that one atom thick layer of graphene was doing the same job as a kilometer thick wall of glass in stopping the helium from going out. It's quite astonishing, isn't it?
Yeah, absolutely.
And you can think of this like, we were talking earlier about helium balloons, Debbie.
Yes.
Tell me what you know about helium balloons when you buy them from the shops.
Well, you get the helium balloons. They're going to be the perfect party decoration because they're going to hold up. They're going to hold up and look lovely the entire time of the party. But over the course of the next few days, they're going to, of course, shrink down to something that you have to get rid of, sadly. And with graphene, it seems to me if you made your balloon out of add a little graphene to the balloon, and you might be able to keep them forever.
Exactly. That is precisely it. Yes. When you buy party balloons with helium in them, they're metallized foil, and the reason they cut the plastic with metal is to try and improve the permeability, but they can never quite do it because helium is a very small gas. It's just a single atom, and it works its way through all the pores in the material and eventually leaks out. So it's very, very difficult to trap. But graphene will do that job perfectly. It will stop helium from going through forever, which is amazing. So you're quite right. If you could make a party balloon out of helium, it would stay inflated forever, never deflate.
Imagine you could have reusable balloons then.
Indeed, yeah. But there is other thing that the team found. When they looked, they found that hydrogen actually did pass through the graphene layer, and this was a real puzzle because the hydrogen molecule is actually bigger in size than the helium atom. So how could this happen? And it turned out that there was the graphene was acting as a catalyst. Now, I could just read the words, but it's probably easier if I stop sharing and show you one of my molecular models again to explain what's going on. So now we've got this. This is the graphene layer, and here we have helium gas, and the helium gas tries to get through, and it bounces out, and the graphene is a perfect barrier to helium. Now, that's fine. However, hydrogen is two atoms stuck together, and those two, helium gas is just one atom by itself. Hydrogen gas is two atoms stuck together, and it's bigger than helium. And yet, hydrogen goes through the graphene. So how can this happen? It's quite a bit of a puzzle. And it turns out what's actually going on is that the bonds between the hydrogen atoms here, that cocktail stick here represents a bond which is shared electrons. When the hydrogen comes down to the surface of the graphene, what happens is that the graphene acts as a catalyst. And what that means is that that bond between the hydrogen atoms breaks and it forms temporarily with the carbon. And then these bonds are never just sort of formed forever. They're constantly in dynamic transition. So what happens is the hydrogen ions, the protons, then they're protons when they're the center of the hydrogen. They'll actually pass through, and then they reform on the surface, the other side. And so the net effect is something bigger than helium can actually pass through, get split apart, pass through the graphene, and come out again. So it's not a perfect barrier to hydrogen. It's the only gas it does that with. And when I was reading this paper, I originally thought, well, graphene, you could coat the insides of containers for the hydrogen economy, because the hydrogen economy is probably coming to make rockets and cars and ships and all sorts of things move around. But hydrogen gas will get through steel containers. So you would think that if you coated the inside of the container with graphene, that you'd stop the hydrogen gas going through. That obviously doesn't happen.
It's not going to work.
Yeah. So you'd think, oh no, we can't use graphene for the hydrogen economy. However, when you read this paper carefully, the scientists make reference to an earlier paper where they actually looked at what's called bilayer graphene. So it's one layer of graphene on top of another. And can you see how when they stack, the layer underneath sits over the hole in the layer above?
Yes.
Yeah, that's called AB stacking, and that's how graphene likes to stack. And so what happens now is that the hydrogen atom, when it's just one layer, can pass through, but when it's bilayer, just two layers, that other one there stops the hydrogen from going through, so it can't get past. So bilayer graphene is the perfect barrier to hydrogen. So we can use graphene for the hydrogen economy, for lining tanks and things like that. We just need two layers of it rather than one.
And now that's an incredible side discovery to the initial one about the impermeability. Incredible.
Yeah, amazing stuff, isn't it?
We're going to run out of superlatives to describe it, honestly.
You'd think we keep running out of superlatives, but we keep on finding more as well. So as Andre said, graphene keeps surprising us. It's amazing.
Yes, it does, which makes work fun. So thank you so much for describing this to us, for the visual aids and everything. It was a pleasure. And we'll see you next time.
Good fun.